Last time we have not finished the lecture about self-supervised learning. We only talked about BERT. Besides BERT, there is another well-known model called the GPT family. So, what is the GPT family? Last time we talked about how BERT is trained. It is trained to do fill-in-the-blank questions. Then how is GPT trained? GPT is also trained with self-supervised learning, but with a different task from BERT. What GPT does is to predict the next token from the given sequence. For example, suppose there is a sentence of Taiwan da shui in the training data. As we give this sentence to GPT, what will happen? We start with a special token begin of sentence. GPT yields an embedding based on the begin of sentence token. Then, we predict the next token. In this sentence, according to its content, what is the next token? The next token should be Tai. So we have our model according to the first token, and the embedded a begin of sentence. Output the token Tai. Let's go more detailed. We have an embedding that is denoted as H. It is fed to a linear transformation and normalized by softmax function, yielding a distribution. This is the same as classification tasks. Next, we want the cross-entropy between the output distribution and the ground truth to be as small as possible. That is, you are going to predict the next token. Followingly, iteratively repeat this process. You gave your GPT begin of sentence and Tai as input, and it produces corresponding embeddings. Then, it is going to predict the next token. You tell it that the next token is 1. Okay, let's keep it going. You give it begin of sentence, Tai, and 1. And ask it to predict the next token. The next token should be Da. Then you give it begin of sentence, Tai, 1, and Da. The next token should be She. Accordingly, it should predict She. In this example, we just use one sentence to illustrate the training process of GPT. Of course, you will not just use one sentence for training. You will utilize millions of sentences to train the model in practice. This is the training process. That's it. The most remarkable thing is that it utilizes tons of data to train an extremely large model. Then see how the model performs in many aspects. There is one more thing worth mentioning. The GPT model is just like the transformer decoder. We know that there are transformer encoders and transformer decoders, right? I talked about this in previous lectures. The architecture of the GPT resembles that of the transformer decoder. However, the cross attention is replaced. It is replaced by a masked attention. In other words, when the GPT is asked to predict Tai, when given begin of sentence, it cannot see the following words. When the GPT is asked to predict 1, given begin of sentence, and Tai, it cannot see the following words and so on. This is how the GPT is trained. What makes GPT famous is that, since it can predict the next token, it has the ability to generate text. If you have GPT predict the next token constantly, then a complete article can be generated. Moreover, whenever I mention GPT, we will have an image of a unicorn. Why do unicorns represent GPT? The reason is one of the most well-known examples of the GPT series is about generating fake news of unicorns. Here's the fake news. Roughly speaking, the fake news is about discovering unicorns in the Andes. What a piece of lifelike fake news, right? Hence, whenever someone mentions GPT, fake news about the unicorn will also be brought to mind. Besides, for a better understanding of how GPT actually works, there is a demo page for you. It is called Talk to Transformer. On this page, since the largest GPT model is not publicly available, the relatively smaller GPT model is used here. This demo page allows you to enter the beginning of a sentence, and it will generate the rest for you. Okay, so this is the brief explanation of the GPT series. We have already known that it can complete a sentence. However, for the human language processing related downstream tasks, such as question answering, how can GPT be used in these tasks? GPT actually uses a different idea from BERT. But I still have to emphasize that GPT can also be used in the same way as BERT. Do you remember how BERT works? Consider there is a BERT model, followed by a simple linear classifier. Then this model can be used on many downstream tasks. Similarly, consider there is a GPT model, followed by a simple linear classifier. I believe it also works. However, there is no additional classifier in the GPT paper. The paper proposes a crazier idea. Why is it a crazier idea? The additional classifier is already used in BERT's paper. If we always use the additional classifier in the paper, no one will think it is a good paper. Another reason is that the GPT model is too big. Because the GPT model is too big, it is difficult to fine-tune it. When we are using BERT model, you will put a linear classifier after BERT model. In this case, the BERT model also a part of the model you want to train. The parameters of BERT model also need to be adjusted. In the homework about BERT model, you need to spend a little time training the model. You don't train the complete BERT model in the homework. So the TA says you can finish the training process in about 20 minutes. The BERT model is already trained before. You do the fill-in-the-blank question with the BERT model. You just need to fine-tune the BERT model. However, it still takes time to fine-tune the BERT model. The GPT model may be too huge such that it is difficult to fine-tune. It may be impossible to train the GPT model for even one epoch. There is a crazier usage for the GPT models. This usage is close to how humans do it. Think about it. Suppose you go to the exam. For example, you take the TOEFL listening test. What happens in your mind when you do take the test? What is the description of this TOEFL listening test? First, you will see a description of a question. It told you that it is a multiple choice question. You have to select the correct answer from the 4 options A, B, C, D. Then give you an example, guiding you on how to answer the question. Then, you see a new question, and hope you can start answering by analogy. The GPT series is going to do the things below. Can this model do the same thing? For example, assuming that you want the GPT model to do translation. You just input, translate English to French. You give the model this sentence first. This sentence represents the description of the question. Then, you give it a few examples and tell the model. See otter then arrow mark. It should look like this. Or, you tell it something like, plush giraffe. After, plush giraffe. It should look like this and so on. Next, you tell it, cheese then arrow mark. And ask it to fill in the rest. You hope that it can generate the translation results. Do you know how crazy this idea is? During training, GPT wasn't taught to do translation. The only thing it was taught is that, given the first half of a text, it should produce the second half of it. It is just like the example we showed you. Now, we directly give it the first half of the text. Like this. And tell it that you are going to do translation. Then we give it few examples. To teach it what translation is. Next, we give it the English word, cheese. Can it generate the results? Regarding the English to French translation? In the GPT document, this is called few-shot learning. But, from the general few-shot learning point of view, it is a little bit different. The so-called few-shot means that it really relies on few examples. So, it's called few-shot. But, it is not a general learning. There is nothing about gradient descent here. During training, we must run gradient descent. There is nothing about gradient descent here. We don't want to tune the parameters of the GPT model at all. So in the literature on GPT, they gave this training a special name. They are called in-context learning. This means it's not a kind of general learning. It didn't even do gradient descent. Of course, you can give GPT a greater challenge. When we took the TOEFL listening test, we are given only one example. Can GPT know it had to translate by just looking at one example? This is called one-shot learning. There is a more crazy one, called zero-shot learning. Give it a narrative, and say we have to translate now. Can GPT automatically know that it needs to translate? If it can be done, that's really amazing. So did the GPT series achieve this goal? This is a question of different opinions. It's not impossible to get it right. But the accuracy is a bit low. Compared to when you can fine-tune the model, the accuracy is a bit low. For details, please read the article on GPT. The third generation of GPT was tested for 42 tasks. The vertical axis is the accuracy. These three solid lines are the average accuracy of 42 tasks. Few shot is included here, as well as 1 shot and 0 shot. The three lines represent few shot, 1 shot, and 0 shot, respectively. The horizontal axis represents the size of the model. They tested a series of models of different sizes, from only 0.1 billion parameters to 175 billion parameters. So from only 0.1 billion parameters to 175 billion parameters, few shots accuracy ranged from 20% to about 50%. As for whether the average accuracy of 50% can be considered successful or not, is a matter of opinion. It appears that the model actually learns some of the tasks successfully. For example, the task of doing addition. If you give it two numbers, it can actually output the result of adding those two numbers together. However, some tasks seem to be impossible for it to learn. For example, it performs poorly on tasks related to logical reasoning. Okay, I'll leave the details of GPT-3 for you to look it up yourself if you're interested. Also, here is a video of a past lesson, and below is the link to it. The examples we have given so far, including the one we were just talking about, have all been related to texts. However, don't get me wrong, the concept of self-supervised learning is not restricted to only texts. In the field of audio or CV, which means computer vision, the concept of self-supervised learning can also be applied to audio or video applications. Nowadays, there are various self-supervised learning techniques, and the BERT and GPT series that we mentioned belongs to merely one of the three methods of self-supervised learning. They belong to the category of prediction. While there are other types, they are out of the scope of this course. The course, which you may find a bit too shallow, is mainly about introducing the main idea of a topic, and leaving the details for you to do further research on if interested. So, these slides are just here to introduce to you this specific section of self-supervised learning. This is just the tip of the iceberg. And there is much more waiting for everyone to explore. Okay, so we won't go into the details of image processing tasks. I will only put 2 slides here to inform you of a very famous method called SimCLR. Its main idea is not that difficult. I believe you can read the paper by yourself to understand it. There is also a strange method called BOIL. BOIL is very peculiar, and we won't talk about it in class. Why? Because I don't know why it works. This method was proposed in a paper published last summer. If this paper had not been published, and a student came to me to share the same idea with me, I will definitely reject his idea. This idea should not work. It should be impossible. This idea seemed to have a huge flaw in it. But somehow, it worked. And achieved state-of-the-art results. Deep learning is amazing, right? So I am going to skip this part. For speech recognition tasks, you can also use self-supervised learning techniques. You can try to train a speech version of BERT. How can you do that? Just look at how the text version of BERT is trained, and do the same. For example, the text BERT was trained to do fill-in-the-blank questions. You can do the same thing in speech recognition. Just cover some part of the voice signal, and let the machine guess what the covered part is. Also, we can let the machine predict the preceding sound signals. Recall that GPT predicts the token that will appear next. You can also use a speech version of GPT to predict the sound that will appear next. So, you can also try the voice version of GPT. Whether it is the voice version of BERT or GPT, there are a lot of related research results. But in the voice field, there is something lacking compared to the text field. The one I think is lacking now is the benchmark corpus, like glue. In the field of natural language processing, there is the glue corpus for text. At the beginning of this course, and this slide, we just said that there is one database of this benchmark, called glue. There are 9 NLP tasks in it. Today, if you need to know whether BERT is doing well, just let it run those 9 tasks and average them. That means the quality of this self-supervised learning model. But so far in the voice field, there is no database for similar benchmarks. So, our laboratory and other research teams co-developed a voice version of Glue. We called it Superb. It is the abbreviation of Speech Processing Universal of Performance Benchmark. No matter what kind of model you used, you need to give it a name. It's the same here. We call it Superb. We are almost done. And the website is ready to use. Once other teams have watched it, it can be published. Although it is not online yet, you should be able to find related links very soon. In this benchmark corpus, there are 10 different tasks. The speech has many different aspects. Many people talk about speech-related technologies. They only know that speech recognition converts voices into text. But this is not the full view of speech technology. The speech actually contains a lot of information. In addition to the information of content, it contains information of what you said. And other information. For example, this sentence. For example, when this person says this sentence, what is his tone? And behind this sentence, what kind of semantics does it have? So we prepared 10 different tasks. These tasks include different aspects of speech. They include testing a model's ability to identify content, the ability to recognize who is speaking, the ability to recognize how he says, even the ability to recognize the meaning behind the sentence, from all aspects to detect a self-supervised learning model's ability to understand human language. And we also have a toolkit. This toolkit contains a variety of self-supervised learning models. And for these self-supervised learning models, they can do a variety of downstream tasks for speech. I put the link here for your reference. I just want to tell everyone that the technology of self-supervised learning is not only used in words. For images, speeches, they still have a lot of space to apply. The technology of self-supervised learning. Okay. For the self-supervised learning part, like BERT, GPT, we finish here.